All right, so the stuff today, like the classifications, some of those are going to be new. Obviously, we already did like the sum of the interior angles, but we're going back through that again. You definitely need that. Yeah, the 180 thing. Yeah. Okay. All right. So what you guys need, we'll fill in this chart because this goes through all the classifications, and you should have pictures with this anyway. So it's on page 125. And I might add some extra stuff to it, depending on how I feel with these.
Can there be a triangle with two right angles?
Then, no.
Oh, I did FML.
Hey, so the examples I do with these guys are not going to be in the book. So when we actually do the problem, so I can show you the different ways that you're going to be classifying these, because you're going to be using stuff we've done in the past to classify them. You're probably going to have to write those down. There's going to be similar problems in the book, but not the exact same ones because I pulled them from a different document. All right, so we'll start with the top. So they're giving you something that's happening inside a triangle, like they're telling you this is a triangle with one right angle. This is one that's got three acute angles, one obtuse angle, so on. All right, so this obviously with one right angle, this is your right triangle. Representation would just be anything we've dealt with already with Pythagorean theorem. Just make sure that when you draw it, you draw a little box in there, right, so that you've got your right angle. Should really throw letters on there. These two, in case you forgot, the two sides that connect to make that right angle are the two legs, right? That is the hypotenuse, okay, the longest side. Of course, it's nothing really new. All right, three acute angles, something like that. I can put measurements in there if I want, like we can make it 55, 45, is that 80? Okay, those would be three acute angles. This one is an acute triangle, so if you have a triangle where all of the angles are acute, it's an acute one. The next one down, when you got one obtuse angle, what do you think I'm going to call that one? Classify it?
No.
Yeah. What? No, obtuse. What's regular mean?
All the angles are the same on the sides.
Yeah. Which we're coming up to it, Tanner. All right, so with an obtuse triangle, again, you can only have one obtuse angle in there because, right, all the angles, even though we're going to go through it in a second, just to remind you, but, right, all the angles in a triangle have to add up to 180. So if I have more than one obtuse triangle, it's no way it's going to be a triangle, or more than one obtuse angle, I'm already over the 180 degree cap. So it's impossible to have one like that. So the obtuse triangles are generally going to have one side that's really long in comparison to the rest. So like, let's say that's 110, and that'd be 20, and that'd be, what's that, 50. Stop. Okay. And I don't like this. You guys really change that out too. Change that out to that. All right. Just because, remember, the naming it, when you name it, you're naming it by the letters. Like if you want to have a column for a name, like this would be triangle ABC, this was triangle ABC, that one was STV, so on. Okay? Don't get name and classification mixed up. I just kind of realized they did that. It's really bad practice. Good job, book. Okay? Yeah. They got paid lots of money to make that too. Smarty pantses. All right, so all 60. So this would be 60, 60, 60. Okay. With all 60, if you're going to classify it, we already went through this name before. Remember, this is equiangular because it's talking specifically about the angles. Even though with triangles, this one leads you also to the one that's down here with the three congruent sides, because in triangles you can't have one without the other. However, since this one's just isolating the 60-degree angles, we're going to call it equiangular. Two congruent sides. A, B, C. This is isosceles. All right, no congruent sides. So if we had a side length that was like 3, 5, and 6, you know what that's called? Huh? That's scalene. So scalene is just mean that you have no sides being the same. Everything's going to be equal. Or I mean different. Same thing with the angles. All the angle measures would have to be different as well. And then three congruent sides. Like I said, this one, these two kind of go together because you can't have one without the other. All right. So three congruent sides is your equilateral, but that shouldn't be a new name. We use that with the polygons as well. Okay. Now, these three, if you notice, you've got three classifications for the side lengths, and you also have classifications for the angle measures. You got four of those. So you got equiangular, you got acute, you got obtuse, and you got right for the angle measures. And then you got isosceles, scalene, and equilateral for your side lengths. So when you classify them, when they ask you to classify them, you're going to pick one of the sides, one of the angles, and kind of put them together. If you've got these two together, generally speaking, right, equilateral and equiangular make it regular. However, most of the time, if I want to reference this type of triangle, it's probably just going to be called equilateral. That's just generally speaking what it comes up to. I could say regular, but like I said, equilateral is probably the way it's going to come about in most of the cases that you see it. Okay? All right, so I'm going to go through this problem. So if you need to, you want to keep track of the examples I do, you're going to have to write these out. But these should be, the few I do here are going to represent the types of problems you're going to see. Okay, so what they're doing in this one, so they give you a term that goes with the type of triangle that's there. They say it's equilateral. All right, which means that if it's equilateral, then I know that this side, and this side are all congruent to each other. Right, they're all the same. Okay? So the actual question is saying how long is each side, which means I need to find the value of n, plug it back in, then I'll be able to get the actual side length. Since these are all equal to each other, it doesn't matter which two you pair up, but you have to pair up two instead of equal to create the equation. Which two you want to use? All right, so 2n plus 15 over 4 equals, and which one? Why wouldn't you just pick 7n? I'll do that, it's fine.
No, I want the hardest one.
I mean, it's fine. It's not going to be, like, it's not necessarily going to be hard. It's just the other one has a 7n with it. All right, so if I go about solving this, do you want me to move an n or, like, the numbers first?
The numbers to make it positive.
So
Add
all right, so I'll add the 9 over 4. Okay? So here's the thing. When I do 15 over 4 plus 9 over 4, right? The denominator stays the same, correct? And if I add the top two numbers together, that gives me what? Gosh, what's 24 divided by 4? 6? All right, so I can take that out now. So if I find to make it disappear and make that 6, because this is, again, 24 over 4. What next? Subtract what? And that gives me 8n. Then do what? Divide by 8, and that is 6 over 8, which reduces to what? No.
6 over 8.
Is
3/4.
3/4. You want to make it a decimal? I don't really care. It doesn't matter. You want to make it a decimal?
3/4.
Yeah, 2.7.
Sure.
And then you just add it back into 7n, because it's the easiest one.
Fine.
And then it's all congruent.
So what's 7 times 0.75?
Something.
Oh, calculator, let's go.
There's one right there.
Guys, everyone should be doing this. If you're doing something else, get your stuff focused. Come on.
5.25.
5 point what?
25.
You can plug it into all of them if you want. Should come out to the same thing all the way around. I'm assuming it does. So it'll be that. If you want to write the justification, you can just say they're all equal, the sides are all equal, therefore I set this up. That's all the justification you need. Okay? All right, so can I go on past this one? Okay, all right, so here's the next one. Again, this isn't in the book, guys, so if you want an example, which is, fairly good idea to have, I would go ahead and write this down. So that we don't get to where you're doing the homework and you just go, I don't know how to do this. And I go, oh, where's your examples? And I go, I don't know.
Or you use YouTube and watch the video.
Oh, you could, but come on.
I forgot. You want to do that now?
No, not right now. Gosh, I can't see that top number. All right, it doesn't really matter. Okay, so one thing to point out, you can go back on the little chart too and add this. So in the problem up there right now with the triangle, they tell you the thing is isosceles, right? So isosceles means that there's two congruent sides. Okay? And the two sides that are congruent are the ones that are not the base. The base is the one side that is not congruent. So the non-congruent side is considered the base. So when they tell me this right here, that the base is AG, that's telling me that this side up here is like the one that's like the odd side out or whatever. I know that these two sides are congruent. When you do isosceles triangles, and I didn't note it, I should have, these two sides are the legs. So if they give you the, if they say one of the sides is a leg, they're telling you that's one of the congruent sides. And that third side, the one that's not congruent, is your base. So therefore, like again, so my justification for setting this up, like when it says justify, I would do something like, hey, this side right here equals this one because they're the legs, and the legs of an isosceles triangle have to be congruent. So x plus 1.4 is going to equal 2x plus 0.1. And that's it. When it says so my justification is I did that because they're the legs, they're the ones that are congruent to each other. All right? So if I go about solving that out, what do you want me to do? What should I do first?
Get rid of the 0.01 right side.
So subtract that. So what's 1.4 minus 0.1? And then what?
And then,
Subtract the x, so boom. Okay? So then now when it asks for the length of each leg, you do not have to plug it into all the sides. I don't care about the length of the base. They're not asking me that. They're asking for the sides that I just used to solve for. Everything's falling apart. Okay, so if I take my 1.3, do you want to plug it into the x plus 1.4 or the 2x plus 0.1? So AM or GM? GM? Sure. So if I take that and I plug it into here, that should give me the same number I get over there. What's 2 times 1.3?
2.7.
And if I add another 0.1 to that, that is
2.7. I did that.
awesome. Which I would get the same thing here, right? 1.3 plus 1.4 is still 2.7. So again, it's like these things are just going to be identifying where to put the congruency mark. So if you didn't put it on that chart, please add that on that one. For the two congruent sides, make sure that you label the two sides we mark congruent on there. Make sure you put those as legs, and put the other side as a base. Okay. All right. So those first two aren't as tricky. This one goes back to something we haven't talked about for a while, though. At least not necessarily. We might just do part A. We might do part B. We'll see. So I got 3 points graphed out. They're asking you essentially, is the triangle that I get when I connect these three, like, is that a right triangle? That's what they're asking. But you have to back it up. You can't just say, it doesn't look like it, and go about your business. You got to figure out if one of those is a right angle, or at least the one that they want to be a right angle is. They're saying that this angle here is 90 degrees. About time, jeez. Took you long enough. Okay, so like, as a side note, the way you're going to have to do this, and again, this isn't something we've done for a while, for that to be 90 degrees, and for you to check if it's 90 degrees or not, and this thing is graphed out, what you're going to do is check the slope of the two segments that are making that right angle. Or at least making the one that they want you to say is a right angle. Okay, so I'm only checking R just because the problem said so. Okay? So now, and the idea is, if they're 90 degrees, that means that they're perpendicular, and perpendicular lines, right, have opposite reciprocal slopes. So if I find the slope of each line, I just have to look at the slope. I don't have to do anything else with them. I'm just going to make sure that they're opposite reciprocals. Which I could technically do. If they don't reduce to the same thing, or if you don't see it right away, you can just multiply them also. If you multiply them together, they'll give you -1. So if you take two opposite reciprocals and multiply them, they'll always give you -1. Now, since it's graphed out, I'm just going to count rise over run. Right? It's going to be easiest. Okay? So from G to R, going this way, right? So it's going down. How many is that down? 1, 2, 3. So 4 down. And then how far this way? 3. All right, so I know GR, the slope is -4 over 3, because it was down 4, and then it was to the right 3. Okay, so now I'm going to do the same thing, but we need to check RT. If I check this one, how far down does that go? From T to down here, how far does it go? Down 5. How far does it go this way? They're not equal. I mean, they're not opposite reciprocals. They're not a right angle. That's all they wanted you to do in the first one. So your answer should be, on that top one, would be no. It's not a right angle. Your whole justification is that these two right here, these are not opposite reciprocals. Whatever. Okay? Huh? Did you? That was good, man. All right. So now, look, if I did part B, which I don't necessarily need to, part B is just saying take this point right here and transform it. So move it this way 1 and this way down 2. Then you would recheck the slope after you shifted it. I'm assuming that if I move it here, I think that, what's it go, 1 and over, that's going to give me a 3 over 4, so it's going to be an opposite reciprocal if I do move it that way. Okay? All right. On to the next thing. Now, we did sums with polygons. We did the n minus 2 times 180 stuff. We had to have this up there to actually go through all that. It might not have been listed as a theorem. You do need to write this down as a theorem, because what we're working towards over this chapter and the next chapter and even the one after that is more proof type stuff. So you need theorems, you need definitions, you need postulates to give you reasons on why you're allowed to do steps. So on any of the problems where you take a triangle, you add the angles up, and they say, why are you allowed to do that? Triangle sum theorem. Okay, that's how you have to reference it. Or you have to actually say it out in words like, all the angles add up to 180 in a triangle. It's a little quicker to say triangle sum theorem, though. Otherwise, that shouldn't be anything new. You've already done problems with that. We did that with the polygon stuff. Okay? What? It's in the book, man. I didn't put the page number up there, though. There you go, 127. It is in there, though. Right there. All right, so look, I'll go through 2 problems with this. One is in the book. One is up here. Actually, you know what I want you to do? I want you to do that one. That's the one. You can do that one. Okay?
Where do you find that one? It's not in the book.
It's not in the book. The second one's going to be in the book. All right, but you go ahead and do the guys. Go ahead and do this one, and then we'll go through it. Why'd you add them together? No. This plus this. Yeah, 180. Correct?
Totally forgot to do that.
Right? So it's 4x minus whatever the heck that is
Where do you
together.
get 4x?
What?
You add all the x's together.
1 plus 1 plus 2.
40 bits.
Right? Then like 164 plus 48, what was that 212? Like that. Hey, so anyway, so that's what you get if you add them all together. That's how you should start it, right? Because they all have to add up to 180. If you go about solving that out, you should get x equals 98. So if you plug them in, angle A, this one was 32. Is M the one to tell? M is 98. And the other one was 50.
I got it right.
So if I'm going to classify this, so one, I got to pick one that deals with the sides and one that deals with the angles. This is an obtuse angle, which makes it an obtuse triangle. All 3 angles are different measurements, which means all 3 sides have to be different measurements. So this is obtuse and scalene. This is what the classification would be. If you had like 2 angles that are the same, that means 2 of the sides are the same. It's isosceles. If all 3 angles were the same, obviously that'd be equilateral. Okay? All right, so here's what I want you to do, because we're working towards kind of trying to do the proof thing. So we're filling the blank, the one that's on here. Because what I want you to have is all these proof things as reference, like the little charts, so that when it comes time for you to do these on your own, you have things to reference. This is on 128, so it's in your books. We'll count this as like the notes thing. All right, so now look, the bottom part of this says like 1 plus 2 plus 3 equals 180, which would be this angle plus this one plus this one. But you go, oh, that's a triangle, so they have to add up to 180. This is like the proof for why they add up to 180, or it's one of the proofs to saying why a triangle adds up to 180. So the whole triangle sum theorem is gone. You can't just say, hey, that's a triangle, they have to add up to 180. This is like proving why they have to add up to 180. At least one of the methods. All right, so if I go through these first two, if I look at what the given is, those are both given to me. Okay? All right, on step 3 there, where they're taking this angle and this one and putting them together to create a bigger one. That's something we haven't necessarily talked about for a while, but remember, if you take two smaller things, add them together and they equal something bigger, you just say it's the addition property or addition postulate, but you have to say what things you're adding. Here they're adding, what is that called right there? That little symbol?
Angle.
So this is angle addition postulate. So again, you'll see that a lot. Now, that doesn't mean every time I see two angles together and they equal a bigger one, it's that. It's just my first step, or this is the first time I'm talking about two angles adding to something else in this proof, so probably that's a good guess. Like when I come down to this one right here, and I look at these two equaling a number, like specifically 180, all right? Now, in the picture, I understand in the picture that this line is here, but since I've created a larger angle, kind of pretend it's gone now. Because if I take this whole angle right here and add it to this one, that makes a line. Okay? Which means that if it's a line, and I've got two angles, that's a linear pair. Okay? Gosh. So if you have a linear pair, but you're using it in terms of like an equation, you say it's a linear pair postulate. So again, it's just taking the idea that I'm taking one angle, another one right next to it that just so happened to make a straight line, and have them equal to 180. All right? Now, from here to here, these are identical statements. The only difference is this got replaced with this. But up here, since I said they're equal to each other, I'm allowed to switch those in and out. That's called substitution property. If you have two things equal, and you flip-flop them in and out, it's always substitution property. You can do it forever. Interchange them as much as you want. Okay? All right. For the sixth step, if you look at where those are, 2 and 4 are right there. There and there. What are those pairs of angles called? I'm assuming, I didn't mark it, but 3 and 5 also fall under there. That's why they're grouped. So this is alternate interior angle. I think it was postulate. I always forget if those are postulates or theorems. But it's alternate interior angles are congruent. From here to here, if you look, the only thing that changed was that congruency sign changed to equals, which the idea here is what they're going to do is they're going to have two things that are equal, and they're going to interchange them in what's up here. This is an equation, so you have to have a step that changes things from congruent to equal. All right, so what'll happen now is this allows me to go back up to my equation that was in step 5 and plug in the stuff that I want to get rid of. All right, but switching from congruency to equality is definition of congruency. And then again, from here, get rid of this, from here to here, they're changing 5 to 2, right? Or no, 4 to 2, they put it in a different order, and 5 to 3, because of what they have right there. So again, this is substitution property. Okay? Now look, this is like proving that theorem that says that the angles of a triangle add up to 180. Okay? Which means if that theorem didn't exist and you wanted to fully tell someone like that these angles added up to 180, that would have to be your long-winded explanation.